Well, of course, I'd like to thank the organizers. It's a great honor to be here. This will impinge on black holes, but it's not primarily about black holes. It's rather about gravity itself. It's been 100 years, after all, since the version of gravity we've all adhered to, and I want to try and propose a slightly different one. The strong, weak, and electromagnetic forces, as we know, are described by non-abelian gauge theories of the Yang-Mills type, and the force-carrying particles have spin 1. Gravity, on the other hand, is described by Einstein's general relativity, and in the quantum theory, the gravitons have spin 2. But today I want to entertain the idea that spin 2 is, in certain sense, the square of spin 1. Or, if you like, gravity is the square of Yang-Mills. Now, if that were the case, we can ask some interesting questions. For example, do gravitational symmetries originate from flat space Yang-Mills symmetries? Or what's the square root of a black hole? Well, I'm going to try and address the first question, and I'll leave the second one to you. Now, when we talk about symmetries of gravity, there's the familiar ones, general covariance, of course. The laws of physics must be the same to all observers. If spinors are involved, we also need local Lorentz invariance. Some theories of gravity involve local supersymmetry, which I've misspelt, I notice. And also p-forms can enter, which have their own gauge invariance. So I'd like to try and describe how, at least to linearized order, these symmetries of gravity originate from Yang-Mills symmetries. Now, there are also other kinds of symmetries. For example, in supergravity, there are non-compact exceptional symmetries. For example, the maximal four-dimensional supersymmetric theory is n equal 8 supergravity, and it has an E7 global symmetry. So you could well ask, if gravity is the square of Yang-Mills, how does the Yang-Mills know about the E7? Because there's no sign of the E7 in the Yang-Mills theory. Well, in addressing these questions, we had to go back and take a closer look at Yang-Mills theories, and we found what I think some interesting results in their own right, leaving aside their application to gravity, and that's to reformulate them in terms of division algebras. The mathematicians, as you know, have 4 kinds of numbers that they like: real numbers with no imaginary part, complex numbers with 1 imaginary part, quaternions with 3, and octonions with 7. And we'll see how these division algebras feature in describing supersymmetric Yang-Mills theories and why they're important for squaring to get the gravitational theory. Then, if I have time, and I probably won't, I'll tell you some of the properties of these theories that you get by squaring have certain properties not shared by other theories, and in particular, there's something called the self-mirror condition and vanishing conformal anomalies. This is, however, in a theory that's not conformal to start with, so it doesn't help, I don't think, with Harrod's problem. And these have a bearing on logarithmic corrections to the black hole entropy formulae. By the way, just a historical note, I first announced conformal anomalies at the same 1974 quantum gravity conference in Oxford that Stephen announced his black hole evaporation paper. In my case, I'm still waiting for Hollywood to contact me about the movie. Now, the idea that gravity is the square of Yang-Mills has been around in various different guises. Most recently, Svi Byrne and his collaborators have been looking at scattering amplitudes and have shown that in a broad class of situations, the gravitational scattering amplitudes are just the square of the Yang-Mills scattering amplitude. So there's something going on. It's not entirely clear if we can articulate it fully, but there's something going on that means, in some sense at least, gravity is the square of Yang-Mills. And I hope today to contribute to that articulation, although there'll still be many unsolved problems. So the idea is we have two Yang-Mills fields, a left-handed one and a right-handed one, let's call them. They can have different gauge groups a priori, G left and G right. And we want to somehow tensor them and get gravity out of it. But that raises certain questions. The first one is, if this Yang-Mills field belongs to G left and this to G right, they're carrying the indices of the corresponding gauge groups. Gravity, on the other hand, is a color singlet in this respect. So where do the indices go? A second question is, what do we mean by this?
When you say left and right, do you really mean the principle of helicity? Or?
No, I just mean two copies, which I'm using the word left and right. I could have called it red and blue or up and down, just to label them. Historically, the string story, you can relate it to left and right moving fields on world sheets. That's maybe the origin of the left and right. But for our purposes, it's just a labeling. And now, a next question is, what does this cross actually mean? For example, does it obey the Leibniz rule, which you would normally associate with an ordinary product? And if it doesn't, why not? Well, I'm going to present a version of an answer to that, which has the virtue that it seems to work, at least to the order that we've taken it. And the answer to the first question is, where do the gauge indices go, is that we introduce a third field, which is a so-called spectator field. It's neither gravity nor Yang-Mills. And it has a bi-adjoint representation, so it has an I index for the left gauge field and an I prime index for the right one. This spectator field was introduced by Hodges and Cacciazzo in their scattering amplitude discussions, and we find it fits the bill for our purposes. The second question is, what do we mean by the product? And the answer that we find to be the right one is that we want a convolution. So the F star G means this, and this is the product we need, A star phi star A. Now, this does not obey the Leibniz rule. The derivative of the product is either the derivative of the first times the second, or the first times the derivative of the second. It's not the sum. And that will be crucial for our purposes. Now, we're going to do supergravity. We needn't do supergravity, but the virtue of supergravity is that it keeps you on the straight and narrow, because it tells you there's lots of rules you have to obey, and you can do lots of consistency checks. And if anything goes wrong, it's easier to spot. When you're talking about gravitational theories and supergravitational theories, you can either talk about fields off-shell or on-shell. On-shell photon, for example, has just 2 helicity states, whereas off-shell it has 3. And so when you're talking about squaring fields to get another field, you have to make up your mind whether you're talking on-shell or off-shell. We'd like to go off-shell, so we don't need to specify what the dynamics of the fields are yet. Our goal is not, in fact, to derive gravity dynamics from Yang-Mills dynamics. That's the next stage, and it's a very interesting question. Our goal is to derive gravitational symmetries, like general covariance, from Yang-Mills symmetries. So we're going to be off-shell, and the 2 Yang-Mills theories we've chosen to illustrate this are a supersymmetric n=1 Yang-Mills theory. N means there's one supersymmetry, which means that the gauge boson has just one fermionic superpartner, the gaugino, chi. But because we're off-shell, this has 3 degrees of freedom and this has 4, there has to be another boson field so that we have 4 plus 4 in total. And so there's a bosonic auxiliary field, so-called, D, that goes with that multiplet. So the left-handed guy is 4 bosons and 4 fermions. Now, we want to get the simplest supergravity theory, which is n=1. And the trick is, if you multiply one n with another n, the resulting gravity has the sum of the n's. So n=1 supergravity, we'd want to tensor the n=1 multiplet with an n=0 multiplet. So the right-handed guy is just a gauge boson and nothing else, with 3 degrees of freedom. So the degree of freedom count is 4 plus 4 times 3 equals 12 plus 12. So if we're going to get a sensible theory, whatever it is, it will have 12 boson and 12 fermion degrees of freedom. Now, it turns out there is such a gravity theory already tailor-made for that. It's the so-called new minimal formulation of n=1 supergravity. It has a graviton and its partner, the gravitino, which have, let's see, the gravitino has 12 degrees of freedom off-shell, and the graviton has 6. So we've got to find another 6 bosons to match, and these are the auxiliary fields V and B, which have 3 each. So there's your 12 plus 12. So the physical fields are going to be the gravity and the gravitino, but there are these auxiliary fields needed to stay off shell, or as the aficionados say, to close the algebra off shell, we need these auxiliary fields. So what's our dictionary going to be? We're going to have a dictionary now that translates Yang-Mills fields into gravity fields, at least at the linearized level. So H mu nu is our linearized graviton. B mu nu is this auxiliary field. And we're going to put them together into what looks like a non-symmetric metric, Z mu nu. And our dictionary says we're going to put that equal to the convolution of A phi A. So you can check the count here. That says 3 times 3 equals 9, 6 plus 3. What about the gravitino? Where's that coming from? Well, it's the gaugino times on the left times the gauge boson on the right. And this guy is the auxiliary field on the left times the gauge boson on the right. So the question we're asking ourselves now is, can we derive gravity symmetries starting from Yang-Mills? Well, it's not essential, but it's useful to put these super symmetric guys in a superfield V, because you can summarize complicated transformation rules in one equation. But the gauge transformations you shift by these functions lambda and lambda bar. There's a global non-abelian gauge transformation, global gauge transformation. And then there's Poincare transformations, translations, supersymmetry, and rotations on the V field. And then the right-handed field has a similar setup. Linearized theory has this funny property that there are two symmetries. There's a global non-abelian symmetry and a local abelian symmetry. And this is how we see it showing up here. And finally, the spectator field transforms in the obvious way. So we're going to plug these rules into the dictionary and then see what comes out. And here we are. We find that the combination of G plus B transforms by d nu alpha mu left plus d mu alpha nu right. The gravitino transforms like the derivative of a spinor, and V like a gauge transformation. This is just a combination of a linearized diffeomorphism and a gauge transformation on the B mu nu field. You put them together and you get this. So here's the general relativity, at least a linearized order, has come out of the Yang-Mills. And here the local supersymmetry has come out, and here the gauge symmetry has come out. So we've got four local symmetries coming from the global Yang-Mills theory. Now, how come where is the locality of the gravitational parameters coming from? They have their own dictionary, just as the fields have a dictionary. And what happens is the Yang-Mills parameters get multiplied by fields to give us local gravitational parameters. And we also get, just for the record, the correct supersymmetry transformations of n equal 1 nu minimal supergravity. Now that was the gravity multiplet. There's a Lorentz multiplet. This omega is like the spin connection. But in a supersymmetric theory, it has its own superpartners, and they transform like this. And we can play the same game of generating the gravity fields from the Yang-Mills ones, but this time it's the Yang-Mills field strength that appears in the dictionary rather than the potential. And this gives you a nice relation for the curvature and the torsion in terms of Yang-Mills. The Riemann tensor, and there's a plus and a minus Riemann tensor because of the plus and minus torsion, the torsion being the curl of the B field. And for the plus torsion Riemann tensor, you get F mu nu phi F rho sigma, and the minus one is the same thing with the indices interchanged. And the torsion looks like this. So there's an obvious consistency check now. Gravity obeys Bianchi identities, and Yang-Mills theory obeys Bianchi identities. If there's any justice, the gravitational Bianchi identity should follow as a consequence of the Yang-Mills Bianchi identities. And again, they do. So that's the good news. The problem is that everything I've told you is at linearized order. And I wish I could tell you that it works to nonlinear order. We're working on it, but we haven't yet solved it. And I don't know whether that's because we're not smart enough or whether it simply doesn't work. But that's clearly what needs to be done next. And then, in addition to symmetries, you also want to know about dynamics. Where does the gravitational dynamics come from? And again, that's something that we're currently working on, and I don't have anything to report yet on that. So that brings me to the end of the first part of my talk, which was deriving local gravitational symmetries by the idea that gravity is the square of Yang-Mills. I now want to come to the second part of the talk, which is global symmetries. And this involves these division algebras, so I'd like to spend a few minutes talking about those. So we have the reals complex quaternion and octonion with 0, 1, 3, 7 imaginary parts. They provide an intuitive basis for exceptional Lie algebras. As you probably know, the Lie algebras fall into two categories. There are the classical ones, like SU and SON, of the kind that typically show up in particle physics. And then there are these exceptional ones, which people have tried to fit into particle physics, but so far there's no experimental evidence for them. And the mathematicians have something which they call the magic square. And it associates with a pair of division algebras a Lie algebra. So C with H is A5, O with O is E8, and so on. And this has played an interesting role in the history of group theory and mathematics and division algebras and so on. So let me just tell you about a relation between these algebras. An octonion has a basis E0, E1 through E7, where the E0 is real and the 7 EIs are imaginary. And they obey this multiplication rule with this so-called structure constants Cij, and the non-vanishing structure constants are when ijk take these indices. And then there's something called an associator, because the octonions are non-associative, and it's non-zero when they take these indices, and this is the dual of the other one. Now, how can I remember those, you say to yourself? Well, there's a nice little diagram called the Fano plane, which whenever you're stuck for the structure constants of the octonions, you can look it up here. It has 7 vertices and 7 lines, and each line passes through 3 vertices, and 3 lines converge on a vertex. So and then you can have an orientation here. So if you go 1, 5, 6, that should be, with any luck, 5, 6, 1, one of the non-vanishing structure constants. And you can do it with any other of the 7 lines. The circle counts as a line. So 1, 4, 2 should be another one. Didn't see that. 1, 4, 2 should be another one. And there it is, 1, 2, 4. 1, 4, 2 would have had a minus sign. Now, this has got nothing to do with my talk, but I just mentioned it in passing that Ferrara and I were looking a while ago at relations between black holes in string theory and entanglement in quantum information theory. Turns out there's some mathematical relations. Whether they're deep physical relations, we don't know. But this particular setup described the 3-way entanglement of 7 qubits. Each line is a tripartite entanglement, and the 7 of them give you this 56-dimensional Hilbert space. We then use similar tricks to solve an unsolved problem in quantum information theory, which is how you entangle 4 qubits. And we wrote it up in Physical Review Letters, and my collaborator noticed, because I don't watch the show, that it showed up in another context. If you notice, here's the equation from Phys Rev, here's the one on Sheldon's whiteboard, and I have to compliment them that they did in fact get the right equation. Sorry? I don't know. But, here's Fano, by the way. I was curious to know a little bit about him. And it turns out his sons are scientists in their own right, Ugo Fano and Robert Fano.
Which one is the Fano factor in ionization and so on? Is that Ugo?
Ugo, yeah. You can, there's something called the Kaylee Dixon procedure, which starting with an octonion, you can write it as 2 quaternions with an imaginary part E3. And then in turn, that quaternion can be written as 2 complex numbers with an imaginary E2. And of course, the complex can be written as 2 reals with an imaginary E1. So you can either think of 7 reals, 4 complex, 2 quaternions, or 1 octonion. Division means that this equation has a unique solution. Associative means this. Commutative means this. As you go up RCHO, you lose one of these properties. They're all division algebra. This one, you lose the ordering, you lose the commutativity, you lose the associativity. And if you try to go beyond O to this guy, you lose the division property. So the mathematics has a cutoff, RCHO, and it turns out that same cutoff shows up in the physics, as we'll see. It corresponds to not going beyond 11 dimensions or not going beyond n equal 8 supersymmetry in 4 dimensions. Now, there's a couple of definitions we need. There's something called a norm, which looks like this. And there's something called a triality algebra, which looks like this. I won't go into the details. But with these tricks, we were able to give a single Lagrangian, which described all these theories. 10-dimensional Yang-Mills with n equal 1, 6-dimensional Yang-Mills with n equal 1, 2, 4, 1, 2, 4, 3, 1, 2, 4, 8. And one interesting thing for the experts, again, the issue is when you have off-shell formalisms, does the algebra close off-shell, or does it only close on using the equations of motion on-shell? And the well-known result is that the half maximal ones, this one and less, close on-shell, off-shell, but the maximal one does not. 8, 4, 2, 1. And in this way of looking at things, the non-closure can be directly attributed to the non-associativity of the octonions, which I think is quite interesting. So I'll spare you the details. We can write down the Lagrangian. And what's the idea behind all this? Well, at the beginning, I told you that the mathematicians had a magic square, which they got by squaring the division algebras. They had a Lie algebra associated with a pair of division algebras. From our point of view, we've got 4 Yang-Mills theories, and I'm starting in 3 dimensions for the moment. I'll go up in a moment. In 3 dimensions, there are these 4, and what we're claiming is that the Yang-Mills squared, the gravity theories you get by squaring these RCHO Yang-Mills, have symmetries which are precisely those of the mathematicians. So the mathematics magic square equals the physics magic square. How does that work? Well, again, I'll spare you the details. Basically, you put the left-handed spinors and the right-handed ones into a column vector, which gives you one of twice the size. So that means if you tensor 2n equal 4s, you get an n equal 8, and so on. And let me just show you the result. And I hope you can read it. It's not very... So we got RCHO along the top, RCHO along the bottom. We're squaring Yang-Mills theories, and we get 16 supergravity theories. And these supergravity theories have various supersymmetries. The maximum one has got 16. This one has 2, 2, 3, 5, 9, all the way up to 16. There are global and local symmetries associated with them. And the punchline is that the global symmetry G that you get in these 16 slots are precisely the entries in the mathematician's magic square. Now, the ones that live along the boundaries here are unique. So if we were going to get any theory at all, we would have to get these. The ones that live in the middle, you can couple to matter in principle, but the amount of matter you get by squaring is precisely the amount of matter you need to ensure that the symmetry group is the one of the magic square. So it all works out very nicely. So there it is again, coming from two different places, mathematics and supergravity. Now, going back to the question, how does the Yang-Mills know about the symmetries? Well, this is the formula you need. It says the gravitational symmetry is made up of the triality symmetries of the Yang-Mills plus 3 times the product. So I think I had on an earlier slide. Yes. Here's the case of E8. The triality algebra for the Yang-Mills is SO8. On both sides, 3 times O times O. You add it all up, and you get the 248 of E8. So in some sense, the Yang-Mills fields do know, via their triality symmetries, what symmetry you're going to end up with in the gravity symmetry. Now, the reason for starting in 3 dimensions was that you get the 4x4 magic square that you can find in the mathematics textbooks. But you can do the same trick in 4, 6, and 10 dimensions, and you get some other squares which are not so famous but equally interesting. In 4 dimensions, you get this 3x3 square. In 6 dimensions, you get this 2x2 square. And then in 10 dimensions, you get the single apex of this pyramid. So we call this the magic pyramid for obvious reasons. And these are the type 2 supergravities at the top. Now, you notice there's a certain symmetry along the x and y axes that's not shared by the z axis, so to speak. E8, E7, E6, F4, E8, E7, E6, F4, but E8, E7, SO5, 5, U1, it goes 2 ways, but not a 3rd way. But there's another game you can play. Instead of squaring conventional Yang-Mills theories, which are conformally invariant in 4 dimensions, but only 4, you can instead square conformally invariant theories in 3, 4, 6, and that's it, because that's the maximum you can have the conformal theory. So suppose we play that game, we get a conformal pyramid. And now something interesting happens. You got E8, E7, E6, F4, E8, E7, E6, F4. Now we go up, E8, E7, E6. Now, if you were Murray-Gell-Mann trying to find the omega minus, you would look at the gap at the top and say it's waiting to be filled. But there's no theory that we know of that could possibly qualify up there, but it's very tempting if you look at E8, E7, E6, F4 this way, E8, E7, E6, F4 this way, E8, E7, E6. If you're going to get anything, it would have to be F4, wouldn't it? So we're speculating that there's some exotic theory that nobody yet knows about in 10 dimensions, which has that as its global symmetry. Well, I could tell you more about anomalies and so on, but that's probably a good time to stop, and I thank you for your attention. Paul.
Is there anything in Yang-Mills theory that tells us
Why
why space-time
space-time?
should have 4 dimensions? So is 4 picked out as a special number when you square and get general relativity?
No, no. I mean, from a super perspective, it would say since you can have super Yang-Mills in 3, 4, 6, and 10, you can have supergravity in 3, 4, 6, and 10.
Right.
At least. In fact, you can have it in up to 11, but it doesn't pin it down to 4, no.
Right.
If you could explain why Yang-Mills had to be in 4, yes, and you could argue, well, Yang-Mills is only renormalizable in 4, but I don't think that's a good argument because the gravity you get isn't renormalized.
Right.
You presented the way the supersymmetry transformations actually emerge on the field from these tensor rings. But for the duality symmetries, you're giving us rather abstract presentation of the groups emerging. Is there a way to actually get the duality transformations out of the fields as well?
You're referring to the, let's go back. You're referring to the dualities that live inside this non-compact G, is that what you?
Yeah, in particular.
Yeah. Yes, Kelly's saying in this, well, let's look at 4 dimensions, that's more familiar. In maximal 4-dimensional supergravity, there's an E77, and there are 28 photons, and the 28 field strengths and their 28 joules transform as an irreducible 56 under the E7. It's an electric magnetic duality because it takes F into its joule. And Kelly's asking, can we see the origin of that from the Yang-Mills perspective? Well, we looked at that, and it's a bit of a puzzle because the only place we could see it coming from was the Yang-Mills dualities. On the other hand, the Yang-Mills dualities are non-perturbative. There's no, the F into F star operation in Yang-Mills is not one you can see in the field, in the classical field equations. But on the other hand, I can't see any other place where it could come from. So that's the best I can answer at the moment. It looks like it's coming from the Yang-Mills duality, but it's strange that a non-perturbative Yang-Mills symmetry is giving you a perturbative gravitational symmetry.
Can you see the distinction between the you have the divisor group, SU8 for the n equals 8 theory, and then you have the coset generators.
Yeah.
So can you see how does this tell you that the supergravity theory should have the 70 scalars? Which
Should
sit in
have?
the 70 scalars that sit in the coset.
Yes, yes, it tells you that because, okay, let me be a bit more careful. What we actually derive, these gravitational theories have scalars that belong in a coset G over H. G is a global non-compact symmetry. H is the local maximal subgroup. So in the case of n equal 8, the global symmetry is E77. The maximal local subgroup is SU8. Now, when we do the squaring, what we actually are deriving is H rather than G, to be honest. That's what we can justify. If we make the assumption that it's a homogeneous space, that uniquely fixes G. But that's an assumption. It doesn't come out of our squaring. So there's an extra step. But if you make that extra step, then it immediately tells you that G over H is 70. And in the three-dimensional case, it was E8 over SO16, so it was 256. Yeah.
We have Yang-Mills theory, so we can perform local isospin rotations. So, right?
What?
So, your two isospin rotations, do they somehow give general coordinate invariance or something?
Yes. That's what we're saying. Let's go back to the beginning. So for the fields, we're saying the field is given by the square of two Yang-Mills with the spectator field sandwiched in between. For the gauge parameters, something similar. So the general coordinate parameter is what you would call isospin times a vector. With the scalar sandwiched in between to soak up the indices.
I'm trying to visualize what these
So let's take the simple case where both left and right is SU2. Okay. So this is an SU2 gauge field. This is an SU2 parameter. And then I multiply them together and soak up the indices with this spectator that's in the adjoint of SU2 cross SU2. And I get a vector field, which is local because this is local. And that's the diffeomorphism parameter of the general coordinate transformation.
But it's not the vector fields of the Thierbine. It's some other kind of vector field.
It's the parameter, not the. I'm talking about the symmetry here. This is the amount by which the metric changes under a diffeomorphism. Is there anything I can do to convince you more?
No, I'm trying to visualize what it could be, what these isospins or whatever it could be.
I mean, I have conceptual problems asking what does it mean to start with a flat space Yang-Mills theory and end up with a curved space gravity theory. But that's what you get. I'm sure there's much deeper questions to be asked about that. But just doing the calculation, this is what we get. Can someone, my hearing's not very good.
It says you're getting flat space gravity, not curved space gravity.
Well, gravity to the linearized order. It's curved because there's a linearized Riemann tensor, as I showed you.
I see. So this was not only at the linearized level?
The Riemann tensor is the square of the Yang-Mills field strengths.
Aha.
Just to come back to this issue of the SU2 indices, that not in direct relation to what Mike's been telling you, but the somewhat analogous calculations of Zwieber and Lenz, Dixon and company when they they obtain supergravity amplitudes, full supergravity nonlinear amplitudes from Yang-Mills. They do it in a color-stripped fashion. They are multiplying left and right, but then they actually strip out the color indices by basically assigning them in a 4-point interaction, colors 1, 2, 3, 4 in a fixed order. So the details of the Yang-Mills group don't really come into it. It just has to be more than Maxwell.
Yeah, which G left and G right you choose seems to play no role in what you end up with. They're arbitrary, as far as we can tell. Yep. Yes.
So if you express the curvature in terms of the matrix, you will see that you get it only at the linear level.
Yes.
I'm sorry, I didn't catch the last part.
Sorry. The curvature can be written as a function of the matrix.
Yeah,
But you got the matrix only at the linear level in terms of the gauge fields.
yeah.
So in that sense, this is a map only at the linear level. I mean, when you write the curvature in terms of the matrix, you have
Matrix, did you say?
metric. The curvature is a function of G mu nu.
Yes.
But you did not construct G mu nu, but only H mu nu, which is a perturbation of the matrix. If I
Yes,
understood
that's right.
correctly. So in that sense, the curvature is the expression for the curvature that is constructed. If you really write it down in terms of the matrix,
Yes, the linearized curvature.
exactly.
Yeah.
So in that sense, it is.
It happens to coincide, as a matter of interest, with the curvature in the freely falling frame. And I've wondered whether that is a useful observation in going to the next stage of nonlinearity.
The second question, are these relations only at the kinematic level, or can you also get them at a dynamical level?
Well, that would be the goal, but at the moment we're being rather modest. We're just trying to derive symmetries. And when we've understood the symmetries, we'll then ask about Lagrangians. But obviously, that's an important question.